Hi, everyone. My name is Alvin. I work at Aurora, and we work on something called the Behavior Data Engine. And so next slide. Today, Katie and I wanted to talk to you about a few opportunities that we'd love for you to be a part of. We think it's an exciting time to join. So I believe most of you, well, first of all, thanks for taking part of your lunch hour or your work day to kind of listen to us talk. I think most of you, if I understand correctly, Shin had reached out to say a lot of folks with, let's say, ML infra or just data infra or just general infrastructure background, but not necessarily, say, machine learning or robotics, let alone self-driving experience, who might be interested in exploring work in this space. I think this would be a perfect opportunity. And so I'm going to spend maybe a few minutes talking about my own journey to explain why I think that's true. So next slide. So just a little bit about me, at least within the past 15 years. So I started my career doing research in distributed systems and generally tried to apply that to things in applied ML, applied AI. And so at the time, the problem really was we have these really interesting large computational problems. And maybe the paradigm there was use cheap commodity hardware. And so this would be what the nature of the problem would be, what kind of software can you build to support solving these problems? And so just for a blast from the past, this might have looked like Hadoop or Spark back in the day, things published in systems conferences, SOSP, NSDI, OSDI, Usenix. Today, I couldn't have dreamed of what it became, but it might be something like what Ray is talking about for many scale and things like that. But at the time, it was really, can we really solve these problems at scale and allow anybody to download open source frameworks to do it? And so I applied a bit of my infra background, but what we realized is we could actually start solving really interesting problems that would impact the real world. And so what people sometimes describe that today as physical AI. And so I joined Uber, which I didn't know at the time was probably a version of that physical AI. And so that company was trying to solve a different problem, which is how can we make transportation as reliable as running water, was one of the old trademarks. And so the problem there was to get someone or something from A to B in the physical world, you actually had to solve a difficult mapping problem. How do I get reliable ETAs, pickups, and drop-offs when I'm modeling the real world? So different from the first bullet where we could be doing, social network sentiment analysis at scale with really complex social graphs. This would be, well, you have to think about the garbage truck that comes on Thursday. You have to think about the fact that a business moved a little bit or that you can't get GPS signal. So the challenges at a technical level were even more. And it was required to kind of ship that product. And so one of the areas I was able to explore was use that expertise I gained from building scalable infra, and then look at the massive data sets we had at Uber and apply ML algorithms to solve some of the pretty low-hanging fruit. I was not an ML expert at the time, but we actually improved trip experiences significantly week over week. And so as we dug into that problem, I was interested in a new problem that Uber spun off a group to do called the Advanced Technology Group to say, well, what else could we do with ML? Is there something we can do to actually further improve transportation and logistics using self-driving vehicles? And so they did have a group that tried to build and then onboard these self-driving vehicles to the Uber network. When I was there, I focused on using the infra and ML background I had to say, okay, what does it take? We're not interacting with human drivers anymore. These are effectively robots. It's a completely different ballgame. So looking at the problems from that lens. Today, Uber is doing some great things. Some former colleagues are getting folks onto their network, but I'm actually really excited. I'm actually at Aurora now. And the thing that's exciting here is that earlier this year, we actually launched a product. That wasn't true when I was at Uber. And we have a truck. You could see the live stream on YouTube in the Southwest making deliveries. And when you ship a product, a whole bunch of new problems come up to solve that weren't there before. And these are pretty real. And so I'm going to talk to you a bit about those today. So I'm going to spend a few minutes just talking about the company and its goals, and then I'll get into the specific challenges. Next slide. Thank you. So the mission of the company is, can we deliver the benefits of self-driving technology safely, quickly, and broadly? And so this ordering is actually very specific. So safety, yes, thank you. Next slide. Safety is the key tenet that all of our decisions and timelines are shaped around. And so specific to trucking, there is an opportunity to make the roads safer. And we can pull out statistics every year, and the trends seem to keep growing. There are over 500,000 crashes on US roads involving these large trucks. And the downstream consequences of fatalities and serious injuries are pretty severe. And if we can avoid that using technology, I think that's a very, very great goal and part of the company's mission. But beyond that, next slide. I've found it very compelling when we're building technology towards a very concrete opportunity. And so within the trucking industry, there are various things that this can do beyond increasing safety. And this slide illustrates 4. There are probably more. So one is, I guess if you're like me, especially during COVID, I had a pile of Amazon boxes just from deliveries that were super convenient. The demand for long-haul trucking and logistics is far outpacing its supply. Truck drivers, we're seeing a shortage, and there is high turnover. It's a really tough job. So can we, using technology, find a way to match the industry's demand for long-haul trucking? And if we can do that safely, we can also do other things, such as deliver these maybe continuously 24/7 and not be limited by the things we need to limit for the safety of human drivers operating behind the wheel, if we can remove that driver for at least a portion. And studies show that, and if we can further automate that, we can do interesting things such as reduce fuel consumption and emissions by up to 32%. There's actually a study, I was surprised by that number as well, but you can imagine, more steady driving, less lower speeds and things like that you can control by wire. And finally, if this is truly safer, I think the effects of insurance costs and other premiums also become lower. So the industry as a whole is very interested. This seems like a transformative technology beyond safety. So next slide. And so in Aurora itself, it's about 1,800 employees. And the takeaway to me here is it feels large enough where you actually have teams investing in building in scalable infrastructure. We have time to think about and build and learn from each other, but it's small enough where there are more problems to solve than people. So the amount of impact a single engineer can make and grow their career is still really big. I have a laundry list of problems, which I won't even be able to present today, but I think it's an interesting time and size for the company. Next slide. So what is it that we're shipping? And so I'm going to refer to the driver a couple times in this talk. And so if you listen to any external communications or calls, the Aurora Driver is the product. And this slide kind of illustrates the components of it. I'm going to focus a bit not on the hardware, not on the data services, but really the self-driving software that goes into it. And again, this should generalize beyond just trucks. I've been in some test rides with minivans, but for reasons I described before, we do focus on trucking. Next slide. So now I'm going to talk a bit about the software components. So this slide and some others might be a bit outdated with our architecture, but it's just meant to be illustrative of the pieces to make it more concrete when I use terminology. Different self-driving companies probably have very similar breakdowns in some ways. So, same principles apply. But imagine this illustrates the things that have to run in real time on the car. There's still software that we write and run that's off-board. So that's also good to just think about as I describe these things. So at a basic level, inside the box, the software on the car has to reason about where it is in the world, and then maybe overlaid over its concept of a map. And those data are input to 3 different components. There's perception, which just perceives what it sees, be it people or actors or things. And then that generally goes downstream to a component called the planner, which then decides based on that, what should I do next? And then finally, it sends it to another component called controls, which says, given that plan, make it happen. And this is all a feedback loop with the vehicle itself. And finally, there is an affordance for a remote assist session in case we get into situations where we do need a human in the loop. Next slide. So today I'm going to focus on really that perception and planning boundary from that diagram. And so this image, it's actually probably a pretty old log, and I don't know if it's a real or synthetic one, but it's of an intersection, and it's trying to illustrate the things from the view of the car. These are returns, and then maybe some inferences of boxes of things that it sees. So the roads, the buildings, people, and then just the raw sensor returns. And so this is the data that it has to actually make sense of, has to do this at scale, has to be accurate, and it has to deal with the long tail of things that might be different in different times of the day or different geographies. Next slide. So if I were to break down these into simple components, perception, you can think of its inputs might be the different sensors. So if you kind of read about, the different companies and their philosophies, they can choose their own inputs, but at some point you have these sensor inputs, right? So for us, we have LiDAR, we have camera, we have radar inputs. We do have a way to represent things like, what's the ground surface? Are we elevated? Are we not? Is there an overpass? Where are we in the world? And then some of the map data I alluded to. So perception will take that data. And then there's a chosen contract here. Again, this might not be entirely up to date, but get the point across. It turns those into what we call tracks. So things that move. So what is that geography and like, where is it going? And then what are the things that we actually can't track, but we're going to track those explicitly. These are the unknowns. And then some other things, they might include things like the traffic lights and what are those states, what's going on there. And so those get further refined and then sent to planning, which then, for the sake of discussion, let's just say these are called trajectories. This is where I'm going to go next. And that could include speeding up, slowing down, or moving somewhere. And so that's what I'm going to refer to as the word behavior. Next slide. So hopefully by the end, you'll understand why the word's behavior data engine. So this is where we think we can use your help. So just maybe a conceptual goal from the company. This is before I joined. The company had a hypothesis that it could put together ML experts and roboticists who are experts in their field, this world-class team. But really, it needs a blend of those experts and world-class software engineers or engineers at large. And so the slide on the left is an example of that idea where, let's say we threw a great ML model at tracking components based on sensor inputs. Well, it could be better if you did good engineering. So on the bottom, it does require a little bit of robotics, but if you build good state estimation based on that ML model output, you'll see that the tracks appear smoother and probably more reasonable to reason about for a downstream component like the planner. And so taking that idea a step further, we believe that better data and infrastructure as we scale our now launched product will be the most important thing for the company moving forward, at least from my perspective. And so the graph on the right illustrates this point elsewhere in industry. So I borrowed this from Andrew Ng. I think he had a couple papers a couple years ago, and he called this data-centric AI. And in this graph, he's just trying to illustrate some learned model. Classifier could be anything, just even simple. There's a trend to say, just give me more data and I'll get better. While that can be true, this also observed the fact that even with less data, if you make that data more clean and more consistent, and probably more important, you can actually see much larger gains in how your model does. So let's get better data. So we believe this hypothesis is true in our world as well. So next slide. So there are two components to this behavior data engine. We're going to improve the driver in two ways. Let's say you build any model or any black box that drives. The first thing anyone knows that they need to build is, give me good validation data. How do I measure how I'm doing right now so I know where to improve? So that's going to be a bucket I talk about, offline evaluation. Then the next bit will be, okay, given I know how I'm doing right now, how do I actually get better? So there I'll talk about some of the data sets and tooling that we need to do to get there. Next slide, please. So for offline evaluation system, this is just one example of many. You can imagine one way to start is, I'm going to drive on the road. Maybe it won't be an auto, but just kind of collecting how I would do in the system. So on the left, you can imagine that is a portion of a collected log with all the sensor returns you saw. And so what we do is we generate a scenario. And so we have a simulation team that works closely with us that can turn that into a replayable scenario using different versions of your software. So if you saw that you detected something or behaved a certain way, but you want to make a change, you can kind of rerun on that and replay that scenario in a simulation. And then based on that, if you're passing or failing, you can kind of see, is your behavior improved or have you not regressed? And so that's let's say a high level flow of taking an example and seeing how you do and building out that test set. Next slide. So why is this hard and relevant to the audience that we have here with our skills? you can imagine this is just one scenario. It is an interesting event, and you're going to choose some of these, but really you want a large suite. So given that we have a product on the road and we do want to expand it, the goal was what, 24/7 driving, for instance, right? We want these robots can keep operating. Well, what if I take that scenario and extend it to a sweep of different times of day? I might have different weather. I might have different lighting conditions. Does that change anything? Or there's an intersection here, but maybe these intersections look very different as I expand the lanes across the country. Do I have variants like that there? So you can imagine now you're going to get an explosion of these variants of things that you want to cover and evaluate your performance. And so what does that look like? Well, some of the problems on the ground, here are just 3 bullets. The first is data modeling. There's this ever-evolving multidimensional space of things that you want to say you have coverage for. Even if you don't have experience in this industry, if you've been in a car or a truck, you can probably come up with a bunch of dimensions you want to test. We need a proper way to model the ontology here, and then have the ability to track coverage and build data pipelines and metrics and things based on this. So this is a huge data modeling problem. The second problem is, right now we are already building hundreds of thousands of these simulations that run multiple times a day. They're very expensive. They take a lot of time to run. The faster and cheaper they can run, the better. The quicker we can get signal from the road. We need to build a platform to support various tweaks to this. And so there's a scale problem here. And just to kind of illustrate this point, I'm reminded of a talk I think Jeff Dean gave, or maybe Google SRE gave, that talked about designing for scale. You design for 10x, but by the time you hit 100x scale, you probably need to redesign. Based on where we're at right now, I'm pretty sure there's a need to redesign our systems. And so there's opportunity there. And third, when we talk about scale, we generally think about volume and throughput and reliability. There's also a bit of a latency aspect. So the moment we see something on the road that we didn't anticipate, how quickly can we turn that into a functioning signal that's reproducible? That end-to-end latency across various workflows is hard. And so the way I think about this is we have to think about which of our workflows are batch versus streaming, and think about how we can up-level things there with that as a constraint. Next slide. So now we've talked about high level, some challenges with getting signaled. So one way to think about this is we effectively wrote a driving test, right? We can see how someone does on the driving test. But how do we actually get better? So next slide. So apologies for these images. Clearly, I'm not a product manager or designer, but this is just the easiest way for me to explain it. So you have all of these scenarios, and you actually want to get better. So an analogy could be you have a driving instructor, and then there's a curated set of lessons that one must learn to help grow my ability to drive in different situations. And so we can apply these in a couple different examples. So next slide. So let's take the first two, expert demonstration and expert feedback. One way to do this is, let's get human experts to drive trucks, log those examples, and have it learn this is good behavior, better behavior, even ideal behavior. Get expert feedback. This is how the software is doing right now. What's the gap between these two? And how you express these is actually quite nuanced. It's not as easy as just, this is good and bad. Like, what is the thing? What is the objective function? How do you measure the deltas, et cetera? So there's a lot of nuance here. But what these two first bullets tell me is you actually need to start building human-in-the-loop workflows. You'll see this classically done in computer vision, where you have labeling workflows, and they call those human-in-the-loop. This is very similar, but from an infra standpoint, now you have to think about, I built this pipeline. These aren't just automated steps that can compute. There's a human in the loop. So do I build a piece with a synchronous component, asynchronous component? It really depends a lot on kind of the interaction and the tooling that the human needs. So there's now a more complicated workflow design. The second is, how do I get better? Maybe I need more examples. I need to understand different construction elements, different types of pedestrian rules. And so how do I get the examples that I need where I'm struggling and where I'm expanded? So there's some challenge there, creating search tooling, discovery tooling. And third, we talked about scale. For test data and training data, there's probably some approximation where we'll need 10 to 100x more training data than we have that driving test data. So all of that pipeline work I talked about, we'll probably need to design for the next order of magnitude as well, or maybe have two. There's a design decision there. Next slide. So overall, hopefully, based on these things, you can kind of see the flow, right? We have examples, we evaluate the system, we try to get it better, and then we see where it struggles, and it comes back in a loop. And so that's why it's called a data engine, and we're specifically focused on the loop of how is the driver doing now? How is his behavior? And so hopefully now we've given you a sense for the problems that we're trying to solve, how you can help, and why it's important. I think the next slide, I'm going to hand it over to Katie to talk about specific opportunities that we're hiring for.
Thank you, Alvin. Hi, everyone. My name is Katie. I'm the recruiting partner for Behavior Data Engineer team. And here are some our opening roles currently that under our autonomy action. And if you see the title towards the end, there is star mark. That means it's under Behavior Data Engine specifically. So I will briefly go over what we're looking for and what level we're looking for about different candidates. So for test automation and behavior coverage, we are looking for staff level, senior level, and software engineer too, for someone who has great experience in data infra and coding Python or C++, and someone if you do have backend storage in cloud, that will be a plus. And we do opening senior machine learning engineer model and validation team as well. For this role, we're looking for someone with machine learning background. If you do have motion planning or behavior planning experience, that's a huge plus as well. And there are more opening role on our career website. You can scan the QR code or just go to our career website to apply or looking for more opportunities there. And next, we're going to dive in on some Q&A here. So I'm gonna read through the question, Alvin. You can answer as much as you can. So first question, Alvin, could you please share more about long tail event discovery and the preventative data discovery?
Yeah, that's a great question. I would say we don't have that fully solved, but we are trying several techniques. I don't know that anyone knows how to fully solve that. There is a long tail of problems. How do you not know what you don't know, right? So one philosophy is you have to invest in both on-road examples and synthetic scenarios you've never seen and come up with a way to build those with high fidelity. And I think a lot of companies, including ours, are building the right tech. The other dimension I want to mention is you look at, maybe there are at least three things you can look at. You can look at reacting to bottom up. These are things that have happened on the road. We proactively detect these things on board to say, oh, there's a weird decision we weren't sure what to do, or we haven't seen this before. Let's flag that. There's another bit that's top down, which is we have a safety systems and engineering team. A lot of folks actually came from industry like aerospace or NHTSA to say, what are the basic ontology of things that a driver has to do in these geographies, and getting those requirements down to say you need to build test coverage for these requirements and pass those. Then the third orthogonal bit, and hopefully that catches the long tail things we haven't seen, right? But we know that as a licensed driver, that's what you have to do. Then the third bit, there's actually an interesting SOSP paper from 2023, I think, about it's effectively open box testing. Your engineers know how you built your system. Try to break it. And so I think coupling those three are a good way forward, but there's always more to learn. So good question. Katie?
Thank you. And next question, how to close performance gap on corner cases?
Yes, that is, if I understood the question correctly. So if assuming you do have the corner cases identified based on that first answer, then the question is, how do you actually build enough offline test coverage and then on-road coverage to do it? So that's actually part of the importance of this team. The company is making a bet that we can churn out enough tests that are also reliable to cover these cases. And therefore, it becomes very simple for an autonomy developer to evaluate every PR. Like literally, it's running against every PR to see how we do. And so it is on the strength of the test coverage from the first bucket of what this team does.
Thank you. And Alvin, do you also consider the behavior of other road users?
Yes. This is an interesting question. It's nuanced. So baseline, yes, absolutely, because the goodness of your trajectory very much depends on your surrounding actors, right? What's safe and unsafe, and do you impose burden on other road actors? So absolutely, when we evaluate every outcome. I think the nuance here is there's a limitation to the fidelity of your simulations, because it's hard to say how would someone react when you do something different. So there's a challenge that maybe the person's alluding to here, that you do have to, how do you simulate those things and make it reactive or open loop? So that's a constant ongoing challenge that we face. But yes, we do. So.
Thank you. And what are some of the biggest challenges of autonomous transportation?
I think the first few questions for sure address some of those. The long tail, how do you close performance gaps? I think maybe the bit I'll voice over just briefly is making it a product is actually really challenging. That last mile of, I can drive safely in these conditions, but turning that into a product that people will use, will it operate under all of these conditions? Can you get pick up and drop off of loads in the right places? And there are a lot of things you haven't seen before. Reliability of the schedule. These are things that human drivers do well or dispatchers do well. So there's this ecosystem of even like thinking about scheduling these things, understanding the loads and what you can take. The trucking industry has attempted to solve. So you do have to solve that last mile of things outside just autonomy, which is part of, I think, the value in having folks who don't have that background come in and help.
Thank you. I think we have 3 more minutes. We're gonna take the last question. What are the characteristic of a successful engineer at the company?
Yeah, good question. So I think usually it's everyone has at least one quote unquote superpower, right? Whether it's robotics, ML, infra, data, something. It's that willingness to actually care about the product outcome, and just dig or learn as much as possible to solve that and map whatever they're working on to the overall problem space. And I think when people do that, they end up working on the right thing, doing the right trade-off between short-term and long-term, and then gravitating to the most impactful problems. And so folks who may not have had all the background, but have that desire to connect it, I think is what I've seen in the most successful engineers here.
Thank you. All right. Thanks everyone for joining us today. Truly appreciate your time to learn more about our behavior data engineer team. And also stay in touch with us on LinkedIn, or you can apply to any open role that you feel like you would be a great fit. The QR code is on the screen, and also you can go to our career website as well. Thank you so much. Thank you, Alvin. Take care, everyone.
Thanks, everyone. Thanks, Katie.